Hello guys, in this video I'm going to show you how to monitor your Kubernetes applications in production. I know monitoring is not nearly as much fun as building and deploying my applications, right? But who's going to save you when you have 1,000 customers who pay you money to use your product and one day all your servers are down and you don't know what's going on? If you don't have customers, your beautiful microservice architecture really doesn't matter. Monitoring answers a very simple question. Is my system healthy or not? And if your system is not healthy and you're not working to fix it, your users will not stick around. So, today you're going to learn how to set up a monitoring pipeline for an application running on Kubernetes. We are going to discuss the most important metrics that you absolutely need to monitor. Then I'm going to show you how to create beautiful and useful dashboards to keep an eye on your system's health. And finally, we are going to create some alerts that don't burn you out. Seriously. Am I the only one who hates on call? Welcome to Kubernetes from Zero to Hero. My name is Raghav. Let's get started. Okay, the agenda for this project is pretty simple. We'll take up a dummy application which is already running on Kubernetes. We will set up monitoring on it. After setting up monitoring, we will start receiving some metrics about how this application is performing while it is trying to serve traffic. What is the health of this application like? What kind of resources it uses and how many errors does it have, how many successful requests it has, and so on. The next step would be to set up alerting on top of these metrics. And finally, we will also send some dummy traffic to the application and see how this traffic actually makes an impact on the metrics and whether this traffic is able to trigger some alerts that we set up or not. The first thing is I want to show you what is this dummy application that we're talking about. Okay, I have already committed this application inside the main repository. When you go inside the monitoring Kubernetes apps, this is a dummy Python application that we're going to deploy, but you don't need to know Python. You could be deploying any other application in any other language and framework. I just took Python as an example. So first things first, I'm going to show you the main application, which is app.py. It is as you can see, a Flask REST API, which serves some endpoints. And the main thing here is, of course, these endpoints and what they do. After registering all these endpoints, I'm just running the server, binding to localhost on port 5000 and just serving these requests. Okay. You will see that each endpoint serves a particular purpose and it is designed so that when we hit this endpoint, it will impact a certain metric. For example, if I hit this API endpoint, random client-side error, it generates a random error with the HTTP status code between 400 and 418 and then sends that back to the client as a response. Similarly, we've got random server-side error, which gives us back an HTTP status between 500 and 508. And we have an unhandled exception route. Whenever I hit this route, it will actually throw an exception which is not handled properly. Coming to slightly more interesting routes, if you see these API endpoints, when we hit these API endpoints, they will do certain processing. Now, internally, all this processing is just useless. We're just using some CPU cycles or some memory. The purpose is to simulate some work being done and to simulate that some API endpoint is very high on CPU usage, but low on memory usage. Some endpoint could be high on both CPU and memory. Some could be low on CPU and low on memory. And then some could be like it somewhat uses CPU and uses very high memory. And I'm also going to show you what these endpoints internally do. If I hit this API endpoint 10 times, my CPU usage will probably be very high and I should see that in the metrics. Let's go back. I'm also going to show you eater. This is the module and I'm defining all these functions which we use in the API endpoints. So for example, for high CPU, low memory endpoint, it's a function which simply runs a for loop, does some random operations and then returns that result. It has a time complexity of 2 to the power n and space complexity of O1. Similarly, if we see high CPU, high memory, this is a function which will take O2 to the n time complexity and then even the space complexity is O n square. So everything is high in terms of usage. It uses a lot of memory because it just generates a string of spaces that occupies n square memory. And it also runs a for loop for 2 to the n number of times and just does a random operation. So the point of these functions is just that we end up consuming some resources and we want this to reflect on our metrics. Up next, I'm going to show you requirements.txt, which is the Python way of defining the dependencies of the application. I only have Flask. Everything else is just standard library. Next, this entire application is also already packaged inside a Docker image. And this is the definition of the Docker image. It's pretty straightforward. I just, take a base Python image. I add my code to it. I add all the dependencies and run python3 app.py, right? So when I start my Docker image, it will just run this command and it will start running my application inside the container. And finally, there's also the API tester. This is going to start making dummy requests to the application with different values so that the application uses different amount of resources depending on which API endpoint you're hitting and depending on N that you're supplying with your request. Then there's these standard API endpoints. If I hit this API endpoint, it's going to definitely result in a 4xx error or 5xx or an exception. Right? It'll keep on generating lots of traffic. This application doesn't exist unless I close it myself. API tester is not going to be part of the Docker container that's running. A tester is something I run separately. Okay, I want to first run this application on my local and show it to you. I am already inside my repository. It's already cloned onto my local. I also already built the Docker container image for the application. I built the Python API 004, which is actually built from this Docker file that I just showed you, right? Let's run it. I'm gonna run my Python API Docker container and expose it on my local at port 8000. Okay, now let me try the API. This is expected because I didn't define any home root. So we just get a 404, which is fine. We got the log for it. Let's try an actual API root /random client error. Okay. I expect that this should return to me some random 4xx error. Okay, that gave me a 404. Oh wait, that gave me a 404 because I used the wrong API. Random client side error. My bad. Yeah, there you go. So once I do random client side error, I got a 410 with status client failure. I run it again. This time I get a 409 conflict, 407. There. Okay. A server side error. Random server side error. This gave me a random server side error, and I also got the log here that there was some server side error, and we returned a 501 once more, 501 again, 505, right? Let's do the unhandled exception. So when I hit the unhandled exception API, it actually broke my entire application because indeed there was an unhandled exception. If it is actually happening to your production application, it's something you need to fix ASAP before your application completely crashes because of one user's request. Let's also test out the resource usage endpoints. Let me pick up high CPU, low memory. Let's say that, right? Resource user. Okay. And I'm going to supply n as 10. It'll take n and it's going to just do 2 to the power 10, and for those many number of times it's just going to keep adding 1 to my result and then just return the result to me. The bottom line is it's just going to do some random processing. So let's do that. Okay, for n I get the result as 1024. I'm gonna remove the verbose. And 10 was easy. The response was pretty quick. I would like to see what happens if I send n equals 20, because as I increase n, what's happening here is 2 to the n increases exponentially. So at some point this should start taking much longer. Okay, so 20 was also fine. How about we use 25? That took slightly longer. 27. Now 27 took noticeably long time, and I'm gonna go up to 30, and this is gonna cause some serious time. And there's not a lot of difference between 27 and 30, but When you do 2 to the power 27 versus 2 to the power 30, that requires a lot more CPU cycles. Yeah, we finally got the result, but it took a very, very long time. So these are the exact same kind of requests that the API tester makes automatically. For example, if I were to run my image yet again, okay, now I'm going to run API tester. As you can see, API tester is making the same requests and my application is logging all these requests over here. Right? So this way I have just automated all these random HTTP requests made. My application will keep working and using some resources to produce some data. Now, I have also already deployed this application to my Kubernetes cluster. I'm not going to cover how the application is deployed to Kubernetes. For that, you can check out another video of mine where I specifically teach you how to deploy your first application to Kubernetes. For the Minikube setup, the Docker image that I built for my Python application, I have already published it to my Docker Hub. Under my repository, Python API 004, it's already published, right? It's already ready to be pulled. It's a public image, so even you could pull it right now. Now, I want to show you how my application is deployed to Kubernetes. We will go back inside the app directory, right? And inside the app directory, I have yet another file called Kubernetes resources YAML. I define all the resources that I created in Kubernetes to deploy this application. Yeah, I created a service for my application which would run my REST API as a service in Kubernetes, exposed on port 8000. I have set the replicas to 3, which means I'm going to be running 3 pods for my REST API. Next, I have also specified the image to be picked up from my Docker Hub repository. So that's it. It's a very simple configuration. Now, the resources of this application. I'm running this application on Minikube. I have a Minikube cluster running on my local with 4 nodes, 1 control plane and 3 worker nodes. Here are the resources I created from the Kubernetes resources spec. These are my pods, and here's my service, resource heater API. I'm also going to interact with my REST API, which is running inside the cluster. And n equals 9. I get the response. It's serving the REST API as expected. Okay, now you fully understand the application, its purpose, and how it is deployed in Kubernetes. Now we're going to be implementing monitoring on top of this. So when we're trying to monitor specifically an application, right, and get the metrics around that application, that particular type of monitoring is called application performance monitoring. It's a very well-known term in the observability space. APM focuses on monitoring the code's performance, the frameworks that you're using, the web framework. For example, if you're using Python, then Django or Flask, or if you're using Java, then Tomcat or Dropwizard or whatever you're using. If you are using Java application, for example, it would also extract JVM metrics. How is JVM performing? What is the memory utilization like for JVM? And you could do APM with lots of monitoring vendors like Grafana, Site24/7, Elasticsearch, Kibana, I mean. In this video, I'm going to use Site24/7 as my monitoring tool. It is easy to understand and I could sign up without using my credit card, so I'm happy about that. This is what it looks like. And once we actually start implementing the monitoring, we'll also start seeing stuff over here. Okay, so now let's see what a typical monitoring pipeline for APM actually looks like. Now, in this kind of a monitoring pipeline, at the center of it is a monitoring solution, right? Some sort of a central monitoring system. So let's add that. This is a central monitoring solution. Okay, this could be Grafana, it could be Elastic. In my case, it's Site 24/7, but it could be any monitoring solution that you're using. Everything revolves around this. Like, this is the solution that ultimately collects all the metrics from all the systems, from infrastructure and applications, and then displays it to us over dashboards and stuff, right? Next thing is we want to monitor an application. So there would obviously be an application. Let's add an application. Okay. And this app is, of course, let's just suppose it's our microservice. It's the REST API that we built and we would like to monitor. It is running inside some sort of infrastructure. In our case, it's running inside a Kubernetes pod. So let's add that as well. Yeah, that's the depiction of a Kubernetes pod. So now what we want to achieve is to ship the metrics from this app to the central monitoring system. Here's what we want ultimately. Now, one important part that enables all of this metrics shipping from the application to the central monitoring system is called an agent. A monitoring agent, which is generally supplied by the monitoring vendor. So for example, if I'm using Grafana, I could be using an agent specified by Grafana, or like if I'm using Elasticsearch Kibana, they have several agents, like FileBeat is for tailing logs, MetricBeat is for metrics, and all that kind of stuff. So another important piece of the puzzle here is the agent. Yeah, I'm going to use this cool guy like this. The agent's job is to collect all metrics from the application, specifically the APM agent. Different agents are for different purposes. The APM agent specifically collects the metrics from the application and from the frameworks. Frameworks or runtime. Runtime means, like, for example, JVM in case of Java applications, or Go runtime in case of Golang applications. It will ship them to the monitoring system. So actually, I should do something like this. So app sends the metrics to the APM agent, and APM agent sends it to the central monitoring system. APM agent can either be a library embedded into your application code, or it can also be an external application which is running alongside your application, and it keeps collecting metrics from you. Or like, in some or the other way, it takes control of your application and your app is running inside the context of this APM agent. Monitoring systems use a push or a pull model. A pull model means that the monitoring system will periodically ask the agent inside the infra for metrics, and then the agent will send it, right? So this totally depends on when the monitoring system will ask for the metrics. And the push model says that the agent will periodically collect metrics from the app and send it automatically to the monitoring system, and the system must accept those metrics. The SaaS solutions, for example, Datadog or New Relic or even Site 24/7, which I'm going to be using, these are push models where the agent pushes the metrics to these because they don't have the permissions to come inside your infrastructure and talk to your private instances. Okay. Now, the APM agent is something very specific to the programming language that you're using for your application. A Golang APM agent could be different, and a Python APM agent could be different, written in that language only for Python applications. For example, Site 24/7 has the APM agent for Python. Yeah. I can see that there are a bunch of APM agents involved, and depending on the language of my application, I could use the appropriate agent. So coming back, this is what at a very high level your APM monitoring pipeline looks like, right? You have an application agent ships metrics to the central monitoring system, and that's how you see the metrics in your system. Okay, draw something around it. And now we can go back. Good. It is time for us to integrate the APM agent from Site 24/7 into our application, right? So I will start by heading to the documentation. Okay. there are like roughly 3 steps. First is we create a Kubernetes secret and we add our API key into that secret. This API key is how the agent will send the metrics to my account inside 24/7. Second thing that we do is we create an init container. In Kubernetes, an init container is something that runs before the main container inside a pod. The idea behind init containers, it can be used to do some initializations, like create some configuration files or do some checks. So any kind of thing. We here use the init container to set up the APM configuration file for the agent, right? So when the agent finally runs alongside our application, this agent is able to find the configuration, which is going to use to monitor this application and ship the metrics to Site 24/7. And finally, we also integrate our agent inside our application's container, and we'll see how. Okay. I'm going to switch off right now. I'm inside the code. One thing you will see is inside the repository, there's the app and there's the solution. The solution directory contains the whole Kubernetes configuration, the final Kubernetes configuration with the APM integration. Of course, you can go and directly check it out, but we are going to do it ourselves to get the feel of it. So let's go back inside the app. For step 1, we're going to create the Kubernetes secret. So we are creating a generic secret and we're going to supply the secret string over here. To get my secret string, let's head to Site 24/7. Developer and device key. Let's go back to device key and I have created my secret. Let's clear this out. Now, just to check, yeah, I have one secret, which I call Site 24/7 license key. Of course, I'm not going to see the secret value by describe, but you get the idea how you can list the secret and how you can get more information on the secret itself. So I have the API key, and this is what my configuration is going to pick up when it's trying to run the agent. Now, let's open the Kubernetes resources manifest and do 2 more configurations. Number 1, let's create the init container. 2 containers, okay, and define my init container. This init container, it's gonna download the APM Docker image from Site 24/7, and it's gonna copy the agent into the main application container that I'm gonna run. So let's call it agent copy init, and the command for it, we can find everything from here actually. Yeah. Image. This is the Site 24/7 Python agent configuration image. Now, we also mount a volume. We'll create this volume. Okay, I just mounted a volume to my init container so that this configuration is copied into the volume, and then it's also accessible to the main container. Okay, but I need to now define the volume. Site 24/7 agent. Yeah. Now, this is my main container, Flask API. So right now you can see that I just pull the image and I start running it. And of course, the image already has the default command of Python 3 app.py. So I don't really need to specify any command. The image will know what to do when it starts running as a container. But now there are some changes that we're going to make. Firstly, command. Yeah. So now in my main container, I'm not going to simply start my application, but instead I'm going to start the APM agent. And I'm going to tell this APM agent to in turn run my application, so that ultimately my app is still running, but it's running inside the context of this agent. And now this agent is capable of collecting all the metrics from my app. I'm also going to give this container the volume. Name will be site27 agent. Yeah. So now you see this site24/7 agent volume is being shared between the init container and the main container. And we copy the configuration into this volume, so it's available inside this container as well. Now, to function, my APM agent needs a couple of environment variables. Let's add those also. Let's see what these environment variables are. Yeah, run command. Value would be python3 app.py. But of course, in production, maybe you're using something like gunicorn to start the application, and you would have different commands. Okay, then we also have license key. Now remember, the license key is something whose value we get from the Kubernetes secrets, right? I'm not going to hard code that. So instead, I'm going to refer to the secret. And expose it as s24/7 license key, which is the environment value that the agent will be looking for. And finally, I'm also going to give the application name. And let's call my application resource eater API. So I've also now added the environment variables, told my APM agent how to run the application, how to fetch the license key, and the name of my application. You can see I didn't have to integrate any libraries into my code. I just had to integrate the APM agent in my Kubernetes configuration itself, which is good. So overall, we added the volume, we added the init container using the volume, and we changed the run command to APM agent inside my main container and added the information that it needed to run properly. Good. We are ready to roll out. What do we have currently? We have a bunch of pods already running. So Kubernetes -f Kubernetes resources. Good. Now let's see what's going on. Yeah, some new pods are starting to come up. So I'm going to do. Yeah, I have started watching pods. It looks like, yeah, initializing, terminating. I'm just going to describe my pod. Let's see if pull image, create container. Okay, so everything went smoothly. I also want to check the logs of my pod. Yeah, this time I didn't directly start my Python application, but rather my APM agent started first, and then that agent started running the Python application. I should still be able to access my API. Let's do that. Actually, I'll just change the port. 49199. 49199. And it works. Yes. So my new API also works, but this time I have APM integrated into my API. So time to actually check. We head back to site24/7. I started getting some feed on my resource API. Oh, and of course, right now there's nothing because I just made one request. And if I start making more requests, I'll start seeing more data over here. Okay, So the best thing to do now is to just run the API tester. So it starts sending some traffic to my application. And then after a while, I'm going to refresh my dashboard here and I expect to see more metrics. Let's go back. Let's begin the API tester. Yep, and API tester. Oh, but I need to update the port in it because I'm hard coding the port. Isn't that awesome? Now, what was the port? 49199. 49199. API tester and begin. Good. Now my API tester will keep running some requests. So I left my API tester on for a day, and as you can see, many requests were made, and hopefully now we should have plenty of metrics. Let's go check it out. Yeah. Okay. So for the last 24 hours, I have quite a lot of metrics data about how my application performed. 16,500 requests made to my application thanks to the API tester. When you start shipping metrics and you open up a dashboard, there's going to be a lot of information thrown in your face. Don't be overwhelmed by it. We will see which of the metrics are important. What are the things you should keep your eye on? And the rest might be just noise that you need to filter out. So I'm going to start with the 4 golden signals. Arguably, the 4 most important metrics that you should be monitoring for your application are called the 4 golden signals. It was coined by Google SRE. And it goes something like this. Yeah. The 4 golden signals are basically the 4 metrics that give you a very good overview of the health of your application. These are latency, traffic, errors, and saturation. I'm going to explain to you exactly what they are and what their purpose is and how to actually monitor them. So let's go to another graphic. Let's write them down. Then comes latency, error rate, and finally, okay, number 1, let's focus on the traffic. Traffic signifies the amount of traffic that our service is actually serving per unit time. In case of a REST API like ours, it usually means the amount of HTTP requests per minute or per hour. But for different applications, the traffic could be measured differently. For example, for a MySQL database, the traffic would be the number of read requests and write requests per minute or per hour, that kind of thing. So traffic is very relative, but overall it means how much load our application is serving at any given time. Traffic is very important because it tells us about the demand for our application. We could also see the trends. For example, last month, how was the traffic? And compared to that, how was the traffic this month? Are we growing or are we shrinking? We can also see trends like peak times and low times. For example, if you are a cab aggregator like Uber, right? Uber would generally see very high peaks of traffic during daytime, like let's say 9 a.m. and in the evening time, 5 p.m. Why? Because a lot of office going people are booking Ubers at that time. Compared to that, Uber will see very, very low traffic during night time because most people are sleeping and only very few people are actually traveling by Uber at night time. So they would see different traffic patterns if they look at like the last 1 week of their graph. So here's how traffic looks like in our monitoring. Traffic is mainly request count, the number of requests we received, and the request throughput. What is the amount of requests per minute that our application is serving as of now? So let's see a breakdown if we click on the throughput. So we can see the traffic, the number of requests served per API endpoint, right? Because of the way my API tester currently works, it distributes, it sends a lot of traffic to all the API endpoints. But if I make a change to exclude, let's say, one API endpoint, let's say the medium CPU, high memory endpoint, I exclude from API tester. This number would actually go down to 0 while the others are still 2K, 2.5K. Then up next is latency. Latency is the amount of time it takes for us to service a request from the user. Latency is a very strong indicator of the experience that the user is having while interacting with our application. And it can also tell us about the bottlenecks in our system. For example, in case of our REST API, what that means is once I, as a client, send a request to my API, right? How much time does it take before I get back a response from my API? For latency, we often define a cutoff. A cutoff means what is the amount of time as latency that is acceptable to us. Let's say I have an application which takes care of some transactions. There is one particular API endpoint which accepts a new money transaction from our end user and processes it. And I want the latency on this particular endpoint to be extremely low, right? So I could give it a cutoff of, let's say, 100 milliseconds. What that means is most of my requests, if not all, most of my requests served on this particular API endpoint should be lesser than 100 milliseconds. And again, for different types of applications, the latency would be measured differently. For a MySQL database, for example, the latency could be measured as the amount of time it took once I sent a read request or a write request to my database until when I finally get a response back, when I finally get either an acknowledgement that your data has been written or the data that I requested for as part of the read query, I get that back. That's the latency I'm experiencing with MySQL database. Now, it doesn't make sense for us to just randomly measure some latency. We often define a specific criteria around it, right? Let's say 99% of all my requests that my API is serving should be serviced under 150 milliseconds. Let's say my API receives a total of 100 requests. What that means is 99 out of 100 requests that I serve per minute should be served in under 150 milliseconds. Now, there is 3 types of latency that are commonly used. These are P95, P99, and P50 latencies. The P means percentile, and this number means 95 percentile. Collectively, if let's say I'm saying my P95 latency should be under 150 ms, this translates to 95% of all my requests should be served under 150 ms, right? So in this example, what I'm saying is my P99 latency should be under 150 ms, where 150 is my cutoff and 99% means my P99 latency. So let's see how we actually see latency over here. The first important metric is the average response time. If you can see the graph here, it shows me what is the response time that the server is taking. And you can see there are a bunch of peaks, right? What that means is during this small period, maybe some of my requests took so high amount of time. For example, 6800 ms, right? That's like 7 seconds almost. So some of my requests took so high amount of time that I got a peak over here, but otherwise my latency remained pretty low, which was like just 30 ms or something. And I could just zoom into that particular latency reading to see more. But the idea is to get the response time. Response time tells us how much time it actually took for our API to respond to my requests. And of course, I select the time frame over here. I could just select last 1 hour and I get like, okay, on an average, 40 ms was good enough. Within 40 milliseconds, my API was able to serve my requests. And I can further break it down into per API endpoint, because some of the APIs might be more important to me compared to some other ones. And there is something very interesting going on here. You can see that some of the API endpoints have very high latency versus some of the other ones have almost no latency. It's like just 1 milliseconds compared to 133 milliseconds. And that actually checks out because the low latency endpoints are the ones which return a response to me immediately. These are either client or server side errors. They just pick a random number and send. Or it is the low CPU, low memory, which is a constant time and constant space complexity algorithm, which does nothing, just returns something, right? That's why these endpoints have very low latency. But the moment we go to these endpoints, which take higher memory or higher CPU, which have higher time complexity or space complexity, suddenly the latency increases significantly. That's the difference that the resource consumption makes when we implement APIs. Okay. And yeah, we also have the top 5 transactions by average response time, which is like showing you your most critical API endpoints in terms of latency. If you want to bring your application's latency down, start by looking at these endpoints. And of course, the way we implemented these are by design consuming higher resources. So we know what's going on, and this is absolutely fine. Okay. Up next, we have the error rate. Error rate defines the percentage of requests that fail. For example, if my application is serving 100 requests per minute, 100 API requests, and out of them, 5 requests are failing, that means my error rate is 5%. And what does failure mean? In case of our REST API, we could say that any kind of server-side errors that occur, if we return a 5xx, then that's an error. That's an error on our part, which we need to fix. That's a very simplistic definition to just say 5xx errors. There could be more errors as well, right? Errors based on policy. Let's say if we have a real-time application and our client requires a response from us within 50 milliseconds, otherwise the whole response is useless to them. It doesn't really matter if we gave the correct answer. We would still count it as an error because by policy, it flopped. Now this is for HTTP API, right? For example, for a MySQL database, errors could look different. Let's say if I sent a write request to write some data, and 99 times out of 100 MySQL could write it, but that one time it could not write it. There was something internally. Maybe let's say there was a disk issue, the disk was full. MySQL could simply not write the data, and it wasn't my fault. Me being the user, it wasn't my fault. I gave the correct query, but MySQL just couldn't write it. That's a failure on MySQL part, and so it has one error out of 100 requests per minute. So that's an error rate of 1%. So for different applications, the error rate can be counted differently. It really depends on your use case. Another example in HTTP API could be an unhandled exception, like one of the endpoints we implemented. Okay. So if we go back to errors, an important metric here is the error percentage. This is the error rate. Now, if we go in here, the only error percentage comes from a single endpoint, which is the unhandled exception. This was the endpoint throwing an exception. And our application wasn't handling that exception in any way. That's why this single endpoint is the reason for all of our errors. Here, by default, we do not define server-side errors as also errors. If I start treating server-side errors also as errors, we should start seeing some error percentage over here. And finally, we have resource saturation. Saturation is a measure of how full your services or how full your infrastructure resources are while trying to service all the requests. So for example, if I'm running my application on a server, I would be utilizing a bunch of resources to run my application: CPU, memory, disk storage, network bandwidth, and all these things, right? While I'm serving more and more requests from the user, my application is going to be using more and more resources. And at some point, one of these or some of these resources will start filling up. Let's say I have an application which takes requests from the user and writes a lot of reports onto the hard disk. And let's say my file system has a total space of 1 terabyte. Given enough requests and report writing, at some point that 1 terabyte hard disk would start to fill up. Maybe at some point it's already 900 GB filled up. At that point, it is very important for me to be alerted that something is about to go very wrong. Once my disk is saturated, my application will no longer be able to write reports, and therefore there'll be a downtime. So resource saturation tells us which of our resources are being utilized in what amounts and which of them need our attention sooner. So another example could be if we are running a Java application, we would also like to monitor the JVM memory being used. If we have allocated 8 GB of memory and 7.5 GB of memory is already being used at the moment, then we need to do something so that there is more memory for the JVM to expand into if needed. The important part here is that we should be alerted before a resource is about to be saturated, not when it's saturated, before. So being alerted when, let's say, 80% of my memory or 80% of my disk is full. That's a good basic alert to have so that you can take some action. Now, another very valuable thing is the instance split up. This tells us how is our API performing per instance of the API deployed. In this case, I'm deploying 3 different instances, 3 different containers in 3 different pods in my Kubernetes cluster. This could tell us a lot about per pod health. Maybe one of the pods is deployed on some very old hardware, and so that particular pod is not performing well in terms of CPU or memory. So that one pod could easily be highlighted over here, and then I could go looking into what's wrong with that particular pod. Now, we have plenty of visibility into our application, right? We have a bunch of metrics, we can keep looking at them, but we should only passively monitor all these metrics to just every once in a while keep an eye on how our application's health is performing. But there would be a few metrics that we want to monitor very closely, because if those metrics are performing poorly, it's a major indication that something is either wrong or it's about to go very wrong. This is where alerts come in. So alert triggers when a certain condition defined by us is met. And then we can decide what to do with that alert. And the condition could be something as simple as, let's say that my error rate is going above 10%, right? That could be a cause for alert. Or my disk is 80% full. That could also be a cause for alert. So we pick up a metric, we set a condition on it, and we alert on it. And there are different ways in which you could set up alert. Roughly speaking, there's like a static threshold kind of an alert, which is what I just mentioned, like 80% of my disk is full, so alert. Or dynamic alerts, where the monitoring system looks for anomalies in my application. For example, my traffic for the last 1 week was stable at, let's say, 100 requests per minute, right? But suddenly my traffic in the last 2 minutes has gone up to 5,000 requests per minute. It could indicate a potential DOS attack. So that's an anomaly alert because I don't define any thresholds, but the moment it sees something very bad happening with my regular pattern, that is a cause for an alert, and we could investigate that. So let's create a simple alert. Currently, we have an error rate of 16.6%. I would like to create an alert, which is if our application has 30% error rate for the last 1 minute continuously, then we should get an alert. So let's see how I can do that. I'll add an error threshold. Let's select error rate threshold. I'm going to remove the other errors. Okay. 30%. We're going to go for a static threshold, and ZIA means the anomaly detection, but for now we're going to keep things simple. Let's select time duration for the last 1 minute. So if the error rate stays above 30% for the last 1 minute, then it's a critical error for our API and we should be alerted. Let's say error rate too high. Okay, let's save. And I'm going to use error rate too high as the profile. Save. Okay. Our error rate in the last half an hour has been 15.5%. Now I'm going to make a simple change so that our error rate shoots up. For that, let me switch off the API tester. Good. Okay. I'm going to switch off everything. I'm going to make a very simple change inside our API tester. I'm going to now only call the API endpoints which cause errors, and I'm not going to call anything else. That means comment out every other thing. And that's it. The only endpoint which will now be called is the unhandled exception, which will always return an error, and that will significantly shoot up our error rate. Yeah. And now the API tester only makes one kind of request, the unhandled exception API endpoint, and that will always return 500. It will suddenly start increasing my error rate. Let's see if that happens. Yeah, the error rate is already increasing. In another 1 minute, I will actually start getting alerted on this. Okay, we are starting to receive alert. It's starting to show us that one of our application, resource data API, is now under critical condition. And if we open it up, in the last half an hour, the error rate actually has gone up significantly. You can see over here, and that's why it's a cause for concern, right? Because within just the last 1 minute, the error rate has been much higher than 30% because the error rate has been 100%. The requests that we are making are resulting in error. So it's a 100% error rate. And therefore it's a cause for alerting. Over here, I'm just showing you the alert in the dashboard, but of course, we could then configure this alert to route to something like PagerDuty so that it would actually ping an on-call engineer in the middle of the night or during the day if they're lucky. And that's it. This is how you integrate application performance monitoring into your Kubernetes application, start receiving some metrics in your centralized monitoring, and finally you decide what kind of alerts to set up. Of course, what I showed here was a very simple alert, but in more complex scenarios, you will have more complex alerts, which depend heavily on what your particular application looks like and what is tolerable for you and for your users, right? Maybe for me, 30% error rate, by the way, 30% error rate is a very, very horrible thing to have in your application. Normally, in big production applications, an error rate of even 1% is considered pretty high because the scale at which you're operating, the number of requests you're serving is very high. In 10 million requests, 1% is also a very high number. So you don't want even that kind of error rate. So yeah, and these were some of the things we covered, the agenda for today. How to set up the monitoring pipeline and the golden signals, how to monitor them, how to alert on them. These were the fundamental pieces. From here on, you build things based on the specific use case of your application. Few more examples of things you would like to alert on are if you're operating a MySQL database cluster, which has a reader-writer setup, right? One writer and then 3 or 4 read replicas. Maybe you want to monitor the replication lag in your MySQL cluster. If the replication lag is too high, it's a problem because you are taking data in to write, but that data is not being quickly replicated to readers. And if there's a network partition or your writer goes down, there's inconsistency in data and you're probably going to lose data that writer has, but readers don't, right? That could be a huge cause of concern, especially if you're running something like a payments application. You can't afford to lose such data. Similarly, if you're running a Kafka cluster, right? Consumer lag is something that people often like to monitor. Consumer lag is the amount of time between when some data came into Kafka versus when a consumer actually consumed it. And if it's too high, if there's a lot of records, there's a high chance of data being dropped from Kafka, jobs not being processed properly. And that's it for this one. I hope you learned something from it. And now you can start implementing APM and monitoring and alerting for your applications. Great. I hope you were able to get some visibility into Kubernetes monitoring. Your assignment for today, should you choose to accept it, is to figure out how to monitor the network traffic of a Kubernetes pod. Let's say there is a payments API running inside a pod and you want to make sure that there is no packet loss during its communication with other pods or outside network. How would you monitor this packet loss? Tell me your solution in the comments below. I also want to hear from you. Are there any topics in monitoring or DevOps that you would like me to cover? Tell me your suggestions in the comments below and I can turn them into very entertaining videos for you. Give this video a thumbs up, and if you're new here, subscribe to my channel. Level up your DevOps game. I will see you in the next video.